So the next topic we have is the adaptive predictive coding. Okay, this is in short, we call it as the APC. So it's actually a predictive measure, right? We try to perform the prediction of the speech signal, right? But not by using the normal prediction what we have used in the ADPCM, right? We'll slightly modify. Okay, so this is adaptive predictive. Sorry, I'll repeat. Adaptive predictive coding. All right, so APC. So this is again we are studying with respect to the speech signal. It's called as adaptive predictive coding, right? So the predictor which we had used earlier, right, was not performing the prediction in an adaptive way. Okay, so what we do, we use a slightly different type of predictor, and that predictor will be predicting the coefficients in a adaptive fashion, right, according to the variation. So we have what you call as an output encoder, right? The encoder's output will be decoded before it is given to the predictor's output. Okay, predictor's input, sorry. So I'll directly go with the, it's very similar, the diagram is very similar to what we had discussed earlier. So I will not discuss more about the diagram. We'll just look at the difference, that's all. Okay, what is the difference between the previous one and the current one? We'll just have to identify that. So that will generate a predictor model. It's called as, it's used in the most of the time. This technique is used for a transmission. Whenever you are sending the audio from one location to other location, we go for the we go for the adaptive predictive coding, right? So most of the time, whatever block diagram we write here is corresponding to a APC transmitter. Okay, the transmitter which implements the adaptive predictive coding. Okay, so the block diagram we are writing here is the APC transmitter. So specifically transmitter, because most of we will not be using this for the saving of the audio purpose, right? We don't do this coding for saving, right? Only for the transmission purpose. So most of the block diagrams we see are only the transmitter part. Okay, so let us say we have the input speech. Maybe we'll try to denote that as a S of t. Right, so this is given to a first circuit. The circuit will perform the sampling of the speech. Right, so this is a speech sampler block. So anyway, we already know that the sampler will convert the analog version into the discretized version, right? So we have the sampler coming. So this sampler's output will be given. Recall the ADPCM block, right, where you had a buffer. Initially, I have a buffer. Buffer is because I'm going to store that samples over there for some time, because the present sample, past sample, the sample before that, etc., are needed for my prediction. Correct? I have to hold it for some time. It's like a memory. Okay, so the next block we are going to use will be a buffer. Okay, it's for the same reason why we used earlier. Now also I'm using for the same reason. Okay, there is a buffer. So let me connect the sampler to buffer. Okay, now next part is actually, right, we have a summing block coming up. Recall the ADPCM, very similar to that. It's a summer block, right? So the present sample may be taken from the buffer and given as input to the summing block, and in addition to this, the other one will come from the predictor. Okay, so I'll, as of now we have not written the predictor yet, so I'll just write an input signal. So it's understood that it has to come from the predictor. All right, so there is a positive and there's a negative sign for the predicted value. Now you see why I have a negative sign over there, because whatever I am generating is an error, right? So present sample minus the predicted sample is an error. So I'll write, say maybe this is Sn, and I'm bringing the predicted part of the speech from the predictor. So I'm writing Sn cap. Okay, so one is positive, one is negative. When you subtract from each other, you can get the error signal. Say let's denote that as a delta of n, delta n. Okay, right. Now output of this has to be connected to a quantizer. Okay, right. So as per, we are following the same rule here. We are going to use a sampler, not sampler, sorry, quantizer, my mistake. I'll use a slightly bigger block here to represent the quantization. So let me write the name here. This is 2 level quantizer. So the quantization can be represented, right, using this. So if I use this kind of notation, this represents a quantizer. So quantizer have, let's assume this quantizer has two levels. One is this level, right? Any signal which falls in the negative region, it will be assigned to that, and any signal that falls in the positive side will be assigned to this. So that's a notation of a quantizer. So we can write the plus q and a minus q over there just to represent the quantization. Okay, right? Recall the output of a quantizer is connected to an encoder, right? So as usual, I'm connecting this to an encoder. So this is the encoder block, and the output of the encoder goes directly to the multiplexer, where you can have multiple predictor parameters coming as an input, and you get a single output that goes to the what you call as a digital, or the channel through which you transmit the data. Okay, so all right, let me try to connect this directly. I'll just give this to the output. So this is going to generate the output. The output in the sense it is the encoded output. Okay, encoder generates the encoded output. Okay, now what we do, we need the predictor part. Okay, so for prediction, let's assume that I have a predictor's output coming here. So okay, so from the encoder, I'm taking one part of the signal and I'm giving it to a decoder part, because inbuilt there will be a decoder as well. Okay, so just remember. Anyway, it's this decoder is not going to be used as a part of encoder. Okay, but this decoder is needed. The output of the decoder is needed to get the work done for the predictor. Okay, predictor has to make a guess, right, depending upon the encoder's output, but encoder's output cannot be directly used because it is in the encoded format. I have to decode it. Okay, so only that's the reason why we are using here. Let's go for a decoder. So there will be a decoder, right, but this decoder is going to be a part of the adaptive predictor network, not the actual transmitter network. Okay, fine. So this is given here. Now this actually generates an output, right? Let me write this way. So it is taken and it's given to this. And here, let me assume that I have another summer block. So if you remember, we had a summer block even in case of ADPCM over here. So this is again a summer block, but we are going to add, right? So one signal is coming from here and another signal will come from the other side. Okay, as of now, let me just write this way. Let me add the component later. So this is also going to come. It's both are added together to get the predictor. So this is given to the adaptive predictor. So previously we didn't had an adaptive predictor here. It was a normal predictor. Okay. So we didn't use the adaptive notations over there, right? You simply use the normal. So this predictor actually gets another input. Okay, so the input is actually going to come from the present and the past values of the speech samples present inside the buffer. So you see we have a buffer here. So buffer is, from the buffer we give the all the contents of the buffer, such as the present value, past values, etc. Up to some n values you can hold over there, because buffer is a fixed size of memory, right? You can have 10 spaces, 15 spaces, or 100 spaces. Maybe you can say that 200 page 256 locations, right? But it is fixed. You cannot access the one sample which is beyond its capacity. If it is 10, only 10, not the 11th, 12th we can. So there is a fixed amount of memory available in the buffer. Using those what you call parameters, we'll call it as a parameters. Basically they are the samples, right? We try to get the samples or get the parameters of the predictor. Okay, so I'll write here. So I'll write like this: compute the uh, compute the predictor parameters. So we have to get this because directly the values cannot be given as input. So for that reason, what we did, we simply passed the values of the buffer into a circuit which performs the calculation or the computation of the predictor parameters. Those parameters in turn will give it to the predictor. So it uses, right, those values to predict something. Okay, all right. And now, okay, I'll give this as a different input. This, because I have to get an output from this. So I'll add possible, maybe like this. Okay, so this is how I'll give another input to the predictor. Predictor takes two inputs, okay, like this, and produces an output. And that output will be given to this. That is the SN cap. Okay, so you can see now the SN cap which we had written earlier comes from this. So the same sample, that is SN cap, will be given as input to this. Okay, so those. So now we can see that the adaptive predictor takes the inputs, right? One coming from the decoder and another part that is coming from the computation of the predictor parameters block. Okay, so we have those inputs coming. Let me try to give a notation here which will help us for the representation. So we had an error here. So as you can see, the error shown here is given as a name, and I think that name is the delta n. Okay, so decoder actually predicts an approximation of that. So I'll write here, this is the delta n cap comes from this. Okay, so that's the output of a decoder, and adaptive's output, that is SN cap, is added with the delta n cap, right, to get a value. Maybe we can try to denote that as a gamma m. All right, so that value is given as input, and it also takes the predictor parameters coming from the compute predictor parameter block. Okay, and it calculates the SN cap, which is the approximation or a prediction value, that is the result of the adaptive predictor, right, which uses the encoder's output fundamentally. Okay, so very simple to the previous discussion, right? But only thing is that we use a adaptive predictor over here for the prediction purpose, okay, which generates the predicted value. Is that okay? All right. Now, so reverse of this is possible whenever this is received. So you see the output, whatever we have marked here, right? I'll just go back. This one. So the encoder's output, right? Whatever we have written here, this output directly goes to the channel. Okay. So that is a channel, right? That's a channel which we use for the transmission, but since it is in the digital format, we can call it as a digital channel. So anyway, so maybe we have studied a varieties of channels possible, right, in maybe other subjects, maybe communication or even the signal processing, right? Varieties of channels we have defined. Any one of them is fine for us. Okay, as of now, let's not restrict this to, let's not go to the concepts of various channels present. So simply I'll write output here just to say that, okay, this is given to a channel. Okay, all right. So the channel, using the channel, we send the uh, encoded data to the uh, encoded data, will send the data through the channel to the receiver. Okay, and let's assume on the other side where the signal has been picked up, right, you need to perform the reverse operation of whatever we have done here in the transmitter. So that will be the APC receiver. APC receiver. Okay, so again one block diagram, right, which is very similar to the decoder part we wrote earlier, right? It's actually a decoder room. Okay, now you see we had directly we have received something, and that received part will be actually first demultiplex. So I'll write the input signal as the digital uh, channel output, in the sense it is received from a channel. As I told you, it's assumed to be digital because we are sending the speech in the digital mode, discretized. So it will first come to a buffer like structure, but we don't call it as a buffer, we call it as a demultiplexer. We have a demultiplexer present. Okay, so this demultiplexer will do the similar jobs as a buffer. It will be the data that is present in the demultiplexer. Demultiplexed outputs can be used for the predictor which we need on the receiver side as well. So if you remember, we had, if whatever type of the predictor you are going to use, that predictor is required on both sides, correct? On the transmitter side as well as the receiver side, isn't it? So that means I'm going to use a predictor even in this location, that is on the receiver side. So when I say I'm using a predictor, I need to predict what I need to predict. I need to predict the values, right? So that values, in order to predict them, I need a adaptive predictor. So right, let's look at the position of a predictor now. So the output of this yeah, so the output of a demultiplexer goes as input to the decoder, because the last part which we used on the other side was a encoder, correct? So when I have an encoder, right, I want to convert, I want to do the reverse operation of an encoder, that is a decoder, isn't it? Okay, so let's give it as input to the decoder. So decoder's output, right, is error. From the error, I need to go back to my speech signal, speech samples. That means to this itself, I'm supposed to perform an addition. So this is plus. Previously on the transmitter side, you did a subtraction. Now, in order to come back, I cannot do the what is called as subtraction. I have to do the addition. So this is also plus. Only that's the difference. So here I'm going to write the adaptive predictor. Okay, so that's the predictor. Now the predictor needs input, right, from the predictor parameter. So you will use another predictor parameters. You can use a computer over here. It's a small device, right, to which can be used to compute the predictor's parameters. Okay, so from the demultiplexer, get the data, and from this itself you predict. So you see, from here I'm connecting to this. This is one input. The other input comes from, okay, this is the output. Okay, from here I'm taking the signal that is required for the prediction part. So this is the input. One input comes from this. So here you see whatever we get is an approximation of our gamma n cap. So previously we wrote a gamma n, right? It's cap. In the sense it is a approximated value. Okay, it may not be exactly matched. Now you see I have digital samples coming here. So I have a question to you now. Recall what we studied in the signal sampling. Okay, you had a sampler circuit which actually converted your analog signal into discrete signal. Okay, now what you use, now you see I have a discrete sample here. That's why I'm asking the question. These are the discrete samples what I have. Okay, so my question is, what is the next component that you can connect so that you get back your speech signal? So I'm going to use a block here. Okay, so recall from the basics and answer me what should be this block, so that my output after this block I'm supposed to get the speech signal back. It's actually I'm performing the reconstruction. So the exact word is the reconstruction, signal reconstruction. So what you are going to use, which block you can use here, so that you will get your approximated speech signal, okay, as the output. So we use a filtering approach for converting or the reconstruction, for conversion of a discrete samples into this into the speech original content. Okay, so this is a simple, I'll write LPF, low pass filter, right? So again, you can do a calculation here, but I'll simply skip that part because that's not our motto. So whatever is the sampling rate here, if you have fs as a sampling rate used in this case, right? So this low pass filter will have a cutoff frequency. Fc is equal to your fs by 2, half of that. Okay, obvious reasons, because you have to match the Nyquist criterion, correct? We know that. Okay. So using this particular technique, you can, right, reconstruct the signals which were originally encoded by using adaptive predictive coding. Okay, so construction, in the sense obtaining the encoded signal, right, using the encoder, or it's called as a transmitter by the various textbooks. Also, you can use the reverse process by using a decoder, but that's called as a receiver in a APC terms. Okay, I hope this is clear. Do you have any doubts with this? Okay, so anyway, I'll share you this document, go through that and get back with doubts if any. All right, so the next version of the APC, right? APC is, as we know now, we are going to use it only for a certain application, not a general application. Okay, the prediction of speech is pretty important, right? And we want to build a technique which is general for every every operation. Like I want to store, right? I want to retrieve the data, I want to send the data, everything. If you want to use a common technique for prediction, then that will be the second technique. It is called as LPC. Okay, so this is the easier technique, which is called as the linear, not adaptive, it is linear predictive coding, right? Again, this is widely applicable for speech. All right, now so I'll try to write a fundamental concept here, right, about the linearity. Okay, so linearity in the sense, right, we try to fit a straight line for our data set. Whatever data we have, we are trying to fit a linear it's a straight line. I just want to fit. It's a general term, not specific to LPC, right? Whenever I see the word linearity or linear, my intention is fit it's a straight line, right, to the data. So in the format y is equal to mx plus c, right? So that means I'll give you an example as well. I'll try to finish this as quickly as possible. So see, I have, for example, let me say this is my input. I denote it as x. These are my outputs y. So let me assume that I have the samples marked like this, maybe. Okay. For a given value of x, I have a given value of y. This can be voltage versus current, right? This can be anything. Okay. Temperature of a day versus, right, the time, maybe you can have anything. All right. So like this, I have various data measured, right? Now I know that if I try to connect everything, maybe, right, my intention is to connect every point, then you see this is going to be a non-linear curve, right? When you see, whenever I am using a non-linear curve, the representation of that is pretty difficult. Okay, maybe you have to use a x to the power 6 plus 9x to the power 5 plus 7x cube, something you may get as an equation. Okay, so that is pretty difficult. Is it okay? Whenever I try to fit a non-linear curve satisfying all the points, it is very difficult. So for that reason, what we do, we try to fit a straight line instead of that. It may not pass through all of them, but you see, it will pass through most of them, let's say. Okay. So the red colored is a polynomial fit. Okay. Fitting of a polynomial. Right. So the blue color, what we see is a straight line. Right. So fitting a straight line is easier. Fitting a polynomial is difficult. Okay. Very difficult. And it is, even if you want to write a code, right, running the code may take more time compared to a straight line fitting. So you might have heard about the linear regression, right? In case of ML algorithms, etc. Right? They're very widely used. So now my question is that why do you need a straight line? Answer is it is easy to fit. Correct? Easy to, once I know this, I can actually predict my next values as well. Correct? You see, right? What might come at any other point? It's easy to guess that. So it's a regression problem, right? I know the data set of maybe so past 10 days of the Indian stock market. What may happen tomorrow? Yes, I can guess, right? What may happen day after tomorrow? If you know the straight line, just add one more day to that. I plus 1 will give you the next price. I plus 2 will give you the day after price, like that. You see, right? That those are the regression problems, right? Anyways, so varieties of options available, but right now I'll restrict to only to the linear bar. Okay, fine. So you might have studied one example of the linear approximation. I think that is the easier one to remember as well. That is the output characteristics of a diode. I think that's the one which we studied at first, right? In the whole engineering, the first concept of linearity was practically studied in case of a output equation of output characteristic of a diode. If you remember, I'll quickly go through that because that helps me a lot to understand. So I have the voltage across the diode, okay, in along one axis, and the output or the diode current is this one. So if you see, this is, it will not conduct until some voltage, but then it will increase in this way, correct? So maybe you call it as a V gamma, some notation, doesn't matter. Okay, so V gamma, whenever the voltage is more than V gamma, current increases, but later on it increases exponentially. But if you remember, we never studied this equation as it is. The original equation, if you see, it is I naught into e to the power something. It is not a linear curve, it's a non-linear curve, correct? Okay, but what we did, we never considered that. We consider that the diode is a resistor. What do you mean by resistor? Resistor V is equal to IR. This should be satisfied, correct? So what is this? If you consider output as I, 1 by R times V. So this is your M. This is the X value and this is my Y value. Y equal to MX, right? I wanted to bring it. So that means I could not consider the curve as a whole. What you did, you split the curve, right? You split the curve in small pieces. What do you call this analysis as? If you remember, you tell me. right? You try to cut the curve into small pieces wherein the curve looks like a straight line for me. You see, within this region, it is a straight line, approximately. May not be proper. Okay, I think my whatever I have drawn is not proper, but you try to make you think that okay, within this one cut, it's a straight line. Next cut is also straight line. So piecewise linear model. Have you heard the name? Piecewise linear. It's piecewise. Every piece is a straight line. Okay, so that's why it is called as a piecewise linear model of a diode, right? So our intention is that whenever I am not able to analyze any curve using a what you call a straight line, you try to cut it into small pieces where it looks like straight line and do the analysis. Okay, fine. Now I'll come back, right? So we are in the speech domain now. So we are looking at the speech. Now the fundamental idea of speech. Now it's like I have speech signal just like this, varying like this. Okay, so it is impossible to write even a non-linear curve, non-linear equation for that, right? It's impossible. You cannot write an equation for speech. That's the very fundamental problem which lies in 1970. Since it is there, since that time it is there, now also it exists. If at all somebody solves this, maybe a Nobel is sure for that. So it's such a complex situation. Okay, we still cannot write an equation for a speech. Okay, so once again I have to make a model, right, that represents the speech. Now the speech has a characteristic that the if you have you come across the fundamentals of speech production in any of the other subjects? May not be in multimedia. Have you studied the speech signal processing as an elective somewhere, or do you have any subject? Huh. Okay, all right. Okay. Oh, okay. All right, fine. So then I need to just tell you one very point about who is generating speech in our body. So the obvious answer will be yes, what you say, who is generating the sound. So that's what we say, right? But vocal cords are not generating not the excitation. They are just modulating. Like some signal comes, right? They are the modulators, right? It's just a modulation that is happening here, so that, right? Whatever we say, okay, the speech which we say we hear, it gets generated. It actually is a modulator. It's not a generator, right? The generator function is the impulses generated from the lung. Okay, lung generates the impulse function. Okay, constant amplitude separated by a distance. Okay, fixed distance. This is the impulse signal. We can call it as I of t in time domain, or discrete Iz. Okay, so anyway, it will be studied in detail, those who take the speech as elective. Okay, so just this is what you need to know as of now. So we'll come back to that slightly later. We have an equation coming up. When I write that, I'll explain this further. Okay, so now my fundamental idea is that, let me say that I have the speech sample. Okay, so the speech samples, I want to denote the speech samples x of n. Let me say that it's already sampled and I have the speech samples x of n with me. Okay, what I want to do, I want to write a linear equation for that. Correct? See, our analysis is linear. I want to fit a linear curve for this. Okay, so now obviously I don't have any other parameters. Only thing I can use is the past samples which I have. Correct? So if I'm trying to process my current sample, only I have access to the past samples. If you are using a computer, you may have you have the access for the past few samples. Let me denote as p. Okay, right? I have p samples with me, x of n minus 1, n minus 2, n minus 3, up to n minus p. All right, say 10 samples I have. I can use the 10 samples to guess my present sample. So how do I write that? It's a linear combination. So if you remember, y is equal to mx is a straight line in one dimension. Are you okay with that? This statement? Y is equal to m into x, one dimension. Okay, because x is my dimension, y is the value. but I can actually extend this in the following format to write a multi-dimensional case: m1x1, m2x2 plus m3x3 for a three-dimensional case, and like that. Okay, are you okay with this? Now you see, I'll write, instead of m1, m2, m3, I will use the value alpha. So this is alpha k into x of n minus k. X of n minus k is my past sample. Alpha k is the m value for that, like m1 x of n minus 1, m2 x of n minus 2. So I'll write alpha k, that's all. Alpha 1 first coefficient, alpha 2 equivalent to m2, alpha 3 equivalent to m3. So I have to take the sum of all of them, right? Because there is a plus in the middle. So that is x of n is equal to, I'll write a summation. So summation k varying from 1 to p, because I as I told, I have p past values with me, right? I have a computer can store only p values, not all the values present. Okay, but you see, whenever I'll go back to my previous example, just to bring the word error. Now consider that I have it, this is my sample. Okay, this is my sample, but you see, my straight line prediction says that this is the sample. Sample's value is over here. Sorry, I think it's not visible. I'll bring it back. Okay, see this value, correct? At a given point, right, my value is here, the x mark, but the straight line says your value here, isn't it? So between those two, whatever you have, whatever is the difference between them, it is the error. So whenever I make an approximation, I bring the term called as error. Every term will have an error associated with that. Are you okay? So whenever I try to represent in this format, x of n, my speech sample using a, right, using a linear equation like this, there is an error associated with that, e of n. Is it okay? Are you okay with the error term now? Because every term which we try to represent like this, right, it has error. It introduces an error, because the actual curve is not a straight line. Actual curve is something which we don't know. But I try to make an approximation. So because of that approximation, I can see that I have this issue. Okay. All right. So that's why there is a error term coming into picture. But now the thing is, I don't want to represent my x of n, but let me shift my concentration from the representation of x of n into the error. Okay, therefore this means the error e of n. See, my intention is to minimize this error, correct? If the error is minimum, that means your representation is very accurate. So how do I write that? I try to write that as x of n minus a summation that is varying from k is equal to 1 to p alpha k into x of n minus k. Are you okay with this? Do you have any doubt? No doubt. Okay. So now what I'm trying to do here, let me try to go back to okay, let me try to write a filter representation so that I can give you a complete block diagram which represents the whole concept. Okay, so I have e of n like this. Let me take a z transform. So if you remember, any function which is given as it is, directly I can take its z transform. So e of n gives me capital E of z. Okay, there is x of n whose z transform, let me denote it as capital X of z. Okay, now what happens to this, the summation part? Can you try to recall and tell me what I'm supposed to write for the summation? So you have studied the z transform, correct? Form is a linear operator. Linear operator in the sense I can write summation as it is. No, nothing happens with the summation. Okay, so summation remains there. So it's still the same. So the summation, all the variable k is 1 to p, alpha will also remain same. This is the if I'll write a function. This is the property. X of n has x of z. Okay, then x of n minus k should have its z transform denoted by z to the minus k into x of z. Right? So that's the property which we are using. Okay, I'll just highlight this for your reference. And okay, I'll write. So this means it is z to the minus k into x of z. Right? Okay, so let me try to write. I'll take a x of z common from this above equation, and I'll try to write the reverse. I want to try to write an equation for x of z. Okay, so this implies x of z is equal to, I have taken the x of z common from the right hand side of the above equation, right? I'll move the remaining term to the other side. Okay, so that will be 1 divided by 1 minus the same summation alpha k z to the minus k into e of z. Are you okay with this? So this is the term what we have. Okay. Now we have another concept, right? This is again taken directly from the concepts of speech. Okay, from the basic concepts related to speech, again, this is directly coming from the speech concept, right? If you try to represent the speech sample, right, but right from the speech analysis, the same speech signal x of z can be represented as, this is what we have to take from the concepts of speech signal processing, where they give an equation like this, that is equal to 1 minus the summation. I'll give a different notation, maybe if say j is equal to 1 to maybe q values, so some coefficient, so cj into z to the power minus j, something like that. We have an equation. Okay, and into ij, sorry, iz. So now you see this iz is the impulses used to generate the speech. So I previously I just mentioned that the source of our speech, who is supplying the energy to generate speech, it is by the lungs. Lungs supplies a series of impulse function. Okay, whenever required, that's the source of energy. That energy gets modulated by the vocal or tract, whatever, right? And the sound box to modulate, right? And we generate the speech, right? So this I of z, compare this equation with the above equation, right? So both are same. Left hand side is still the same, the speech. Okay, but the right hand side we can try to, now why we wrote like this, because right, the error function whatever we were trying to model so far, right? So that is actually happening, right? It's equivalently, it's the source of your energy, right? Source of your speech, right? They are similar, correct? So there is actually a further in-depth analysis possible related to this, and we'll derive the concepts called as a formant frequencies. Everybody talks at a unique frequency, right? So when I speak, my formant frequencies, two frequencies will come, at least two dominant frequencies. Okay, so everybody talks with the two frequencies at least, right? Out of which dominant are only two, you get many frequencies, right? So those values are derived from this concept, but as of now our intention is not to do that. I'll not go in depth about that. I'll deviate from here and I'll come to the block diagram of the LPC. Okay, so how do you go ahead and how do you represent the LPC? Now you see you have the E signal, so our intention is this. I'll quickly tell what we are trying to do here. This is there, this is also there. I want to write x of z in terms of E of z. Only thing unknown to me is this alpha values, correct? I don't know what are the alpha values. If you know that, you can use E of z to get your x of z, correct? From the error signal, I can directly get my x of z. Does it make sense? If I want to get my x of z from e of z, right? The unknown terms are only these are alpha k values, right? K varies from 1 to p, right? I should find out all the alpha values, right? So that is k is equal to 1 to p. I'll just write that. Okay, so now how do you find out that? The analysis is a linear prediction analysis. You should fit the curve, that's all. It's a curve fitting type of issue. Okay, so let me try to write a simple block diagram which can be used to do that. Okay, so let me say I have the speech signal. Speech samples, let's try to denote that as x of n. So this is the block. We have a few parts. This block is further subdivided into two parts. So I'll write a bigger block. I give speech samples as input, that is x of n. So one part of the block is the linear predictive analysis part. Okay, linear. So ultimately you see it is nothing but finding out the m values. Sorry, not m, alpha values. It's like m1, m2, m3, m4, whatever we had, right? So corresponding to that, I have alpha 1, alpha 2, alpha 3, alpha 4, etc. Isn't it? So those are the values which I'm supposed to find out, which will be done inside this particular block. So how can we do that? We know how to fit the curves. Curve can be, you can fit a curve to do that. Okay, in addition to that, we normally, whenever we are dealing with the speech samples, right, it is not just enough if you find out the, if you predict these values. In addition to that, I need to get few more details. Okay, so that is called as okay, we can use the, there is a another part related to speech called as a pitch predictor. Okay, then you also need amplitude of speech, etc. Right, we can use a detector circuit for that. Okay, now so ultimately what happens here is this: it generates, the first block actually generates a number of, right, alpha values. So let me try to write a few of them here. Okay, this is the first one, the second one, dot dot dot, I'll get say p different values. Okay, so this is alpha 1, alpha 2, dot 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 dot, alpha p, right? This is what was our requirement. You use a linear predictive analysis to get the various alpha values so that you can try to write an equation for x of n. All right, then you try to club them together to perform what is called as a polynomial factors or factorization, right? This is what will be done. In the sense, I'm what I'm supposed to do, you just, let's go back to the equation. So this whole term will give some factors, correct? So I have 1 minus alpha 1 z to the minus 1, alpha 2 z to the minus 2, plus alpha 3 z to the minus 3. Can you see that, right? So that's the summation, right? So that summation, I can try to perform a factorization. That's what will be done here. So the output of this will be the formats, right? As of now, you don't have to worry about that. That's not a part of our concept, right? But this output is called as a formant parameter. You can try to do analysis which is useful for speech processing. That's one thing. And again, I have some outputs possible here. One is the amplitude of your speech. Okay, and second output is called as a pitch of your voice. Okay, then you can actually find out what whether the input given x of n is given to this block, right? Whether that input is a voice or it's simply noise. Okay, we call it as unvoiced, etc. can be calculated by using this linear predictive analysis, right? For that reason, I just have to do one thing, right? That is my equation: 1 minus summation k is equal to 1 to p alpha k z to the minus k is there, right? Which I'll try to write in the following notation: alpha 1 z inverse minus alpha 2 z to the minus 2 minus alpha 3 z to the minus 3, and so on. It will go like this. Okay, this needs to be factorized for this inside this block. That's what is the factorization, right? You get the alpha ones, get the factorization, then you go ahead and build the applications called as the formant analysis parameters of the speech. Okay, so ultimately the concept is pretty simple. You have to use the past past p samples of the speech to represent the whole data set with a straight line, right? The straight lines, the slope of the line is normally denoted by n. Here we use alpha. Okay, using p number of samples, you try to calculate p different number of slopes: alpha 1, alpha 2, alpha 3 up to alpha p. Okay, so use them for the analysis of speech. So now you see, you don't have to represent all the n values here. You just need the p values. Okay, just you need the past p values to represent the whole speech. That's why it is called as a linear predictive coding. You do a prediction and you try to represent your code.